Hello. Good evening, everybody. Thank you for coming. We have another exciting Stockholm AI / EQT event here, and we have also a guest from all the way from Germany / France, Pruna AI. I'll just give like just a quick introduction to Stockholm AI, then I'll hand it over to Mats Olof over there. We'll talk a little bit about EQT Ventures and then introduce our guest Bertrand tonight. So Stockholm AI, well, maybe I should actually go to this slide. If you're not a member, you just scan that QR code and you can become one for free, right? Cost you nothing. Stockholm AI is a community built about 7 years ago by a bunch of people that today run AI companies or work at DeepMind and Facebook, etc. So the whole idea behind Stockholm AI is that we try to democratize machine learning, data science, artificial intelligence in the Nordics and more specifically in Stockholm. Build a community so that the community can build incredible things and deliver value to the world. So yes, if you are not a member, then join today. We have some sponsors as well that we'd like to thank. So Telavox provides us with a little bit of money every year so that we can buy food and drinks and things like that. Today, the event is actually sponsored by EQT Ventures, and EQT is also our venue partner. So Gabriella, who's a site manager here, she's very kind and allows me to host these events in these beautiful offices here. So yes, and so Stockholm AI doesn't do just events. We also do mentorship programs. So if you want to upskill in AI, if you have some business ideas or things like that, then we have a wide range of expertise that can help you as well. But yeah, I think I'll hand it over to Mats Olof. We'll talk a little bit about EQT.
Thank you. I'm not going to bore you for that long. I'm just going to mention that we're EQT Ventures. For those of you who do not know what we're doing, we invest in early stage companies, mostly tech. Since this is an AI crowd, we also invest in AI companies, one that you will meet quite soon. We're kind of building up our skill set in investing in AI. It's something you learn by investing and meeting a bunch of companies, and Pruna is one of them. So I'm really excited about today's presentation and what they're going to talk about. Just quickly, I've been to quite a few of the Stockholm AI events. So when the opportunity was given to sponsor one of them, I cut the line and grabbed that opportunity to get to meet you all. I hope you enjoyed this event, and I hope that you remember EQT Ventures after it. So without further ado, this is Bertrand. I warned him that I was going to butcher his name.
That was good.
Yeah, thanks.
Okay, so we'll just share my screen first. Perfect. Okay, I think it works. So thanks everyone for joining this session. So today I'm going to talk about just a simple question. So how to make inference of deep learning models more efficient. So let's start with just some basics. So first, how do people use deep learning models? So of course, there exist many tasks in where deep learning can be applied in companies. And this is because there are many different types of data and applications. So for example, you can apply those in images, where basically you can segment cancer or even generate images with models like Stable Diffusion. You can apply these models on videos, for example, when you can track objects on videos or generate videos with models like Sora. You can apply them on audio, where you can transcribe from audio to text with models like Whisper. You can apply them on text with models like Llama, where you do some question answering. Or you can also just do drug discoveries with models like AlphaFold that you might know, that allows to know how proteins fold on themselves. So of course, like all these models, they have some different aspects, but they share some common also themes. And the main ones is that they have like some common phase in their development. So there are like 3 main development phases. So there is actually the development phases itself, where the engineering design the architecture of the model. There is the training phase, where the the engineers train the model weights and try to learn the model weights so that it does some meaningful predictions. And there is the inference phase where the model is deployed and really solve the real task in the real world. And in this presentation, while we can make also the development and the training more efficient, we'll focus actually first in this inference phase, because it represents in the real world like 80 to 90% of the deep learning workload. So that's why we'll focus on this specific inference phase. Now that we know how people use deep learning models, the next question is why do we need efficient deep learning models? So there are like people often say that they like to have things efficient, but it's often in very different contexts. And so this can have very different meanings, and we need to make clear what are the cost and use cases reflected when we talk about efficient machine learning. So a first context, for example, could be about money. For example, some people, they have like a budget constraints. And for example, we work with some companies that very quickly get, cloud compute bills of, $400,000 per month. So this is something that's very important for them. It can be about time. So you want to have very fast models to have like real-time, very good user experience or real-time reaction. And for example, it's very important if you think about like an average internet user as like attention time span of less than 8 seconds. So you really need to have like a very quick generation for the models. You can also think of this in terms of memory. So often what you want to do is actually you want to fit the models on very small device like phones, so that you don't share information with your servers, or you keep also the privacy of the data in the right way. And this is very important because if you think about the latest Llama models, if you take the best ones, it makes alone almost 1 terabyte, and in your phone you have just 8 gigabytes of RAM, 8 gigabytes in terms of memory. So you have to compress it, otherwise it will not fit. But even with compression, sometimes it can be challenging. And last topic is, of course, about energy and CO2 emissions. So in this case, we don't want to waste resources. And one statistic that I give quite often is that if everyone in Germany, for example, would generate 5 pages with ChatGPT, we would need just 2 nuclear plants to generate enough energy for this. So it shows that if you do not care right now, at some point, some people will care about this problem. So hence, to match these efficiency expectations from real-world applications, actually, it's important to follow the right metrics. And the question is, what are the good efficiency metrics? So there are many efficiency metrics. Some of them are called flops, number of parameters, and so on. But actually, while some of them, they can correlate, basically, if you save time, basically you can think, okay, I will save also energy because I use my GPU or my hardware a bit less. Sometimes also they are a bit contradictory because when you make models smaller, you can actually get a slower model as well. So you need to make that clear that you need to focus on the right metrics. So that's why here, when talking about efficiency metrics, the main message is really this should measure the real, real application cost that you care about. And when using this metrics for money, time, memory, or energy, basically what we can realize is that in many cases, like machine learning models require more and more compute and resources. Again, another statistic is to generate just a single image, for example, with stable diffusion or just 1,000 tokens, you require the energy that is in one smartphone. So you cannot, again, there is a problem here, and this increase of the required resources happens while, on the other end, the available resources that you would like to use actually decrease. So beyond the environmental friendly considerations, usually people, they want to have like the smallest model as possible, to have them on smallest hardware at the lowest cost. So this is really things that matters for them. So now, before making the deep learning models more efficient, a question is, how does the deep learning model work? And then we can think of what are the parts that make sense to make efficient or not. So as I was saying before, there are many machine learning models, and usually they share like a common, way of working. So first they take some input data. This input data usually are inputted into some linear transformation with matrix multiplication. And then we do some nonlinear transformation, and we just repeat these operations again and again, before finally just getting like the final prediction output that could be also of any types. So while usually different models, different how these blocks are arranged together, they share, common, concept with these core building blocks, which are matrix multiplication and nonlinear transformation, which are run, on some language, programming language, and some specific hardware. So beyond the language and the hardware, the most critical part of the model is actually the matrix multiplication part, which usually represents 80 to 95% of the deep learning workloads. That's why in this presentation we will focus actually in how to make this part more efficient. So here in this slide, I just showed you some very nice design of different families of compression methods. And there are actually many of other compression methods that exist, but in this case, as I was mentioning, we'll just focus on pruning, quantization, and distillation because they really focus on making this matrix multiplication more efficient. But keep in mind again that there are many other ways, and this is not only the only way to do it. So now we can just start with how to prune deep learning models. So the basic idea with pruning is just to try to remove the less important component of a model without affecting the model quality. So usually there are like three main steps. The first step is just to assign like an importance score to every model weights, which is represented as a square here. Then we just rank all the model weights depending on the importance score that we assign to them. And finally, we just remove the weights which have the lowest importance scores. So this sounds easy, but actually there are a lot of practical questions behind this to make it work properly for different machine learning models. The first question is, what structure should we prune? So a way to do it is to do what we call unstructured pruning, where we just remove individual weights, so individual rectangles here. But this does not provide speedups out of the box because basically you still have the same size of matrices. And so you would still have the same size of matrix multiplication. So what you can do instead is do structured pruning, where you delete like full rows or full columns, where basically you will reduce the size of the matrix multiplications and then get out of the box speedups, for example, on GPUs. The downside is that then there is some dependencies between different layers because you want the dimensions of subsequent layers to match. So make it very complex to prune without breaking the dimensions constraints. Another important question is how to score structures. So again, there are many different important scores to score structures. A naive way would just be to randomly prune structures, and this can work a bit, but of course there are some more involved way. For example, you can score weights based on the magnitudes, so the value that they have, based on higher order informations like gradient or Hessian, which are supposed to represent better, the model dynamics. But in this case, again, you have to trade off between the complexity of computing something like a Hessian, which is really computationally intensive, and having a very naive and quick solution like random pruning. So the next question is actually what sparsity to prune. So usually it's a very normal question. So of course you cannot prune 100% of the model, otherwise you don't have a model anymore. So you don't have like good predictions, and it's very, very bad. So actually there are like some theoretical work to show how much you would lose depending on how much you prune. And in most cases, actually, the optimal pruning ratio depends on the loss curvature, which intuitively is basically related to the complexity of the task you try to solve. So if the task is more complex, of course, you can prune less than if the task is simpler. Another important things to mention is that you can also prune like different layers at different ratio. So you don't have to prune, every layers at 50% if you want to put at 50%. And there are also some works showing that, for example, it's better to prune a bit more the last layers and maybe some early layers, but the layers of the middle are more important. which are called homogeneous and heterogeneous pruning. And then the last question, practical question for pruning is when to prune. So there are like different also considerations to make here. So usually what we observe is to have like an over-parameterized model helps to get, a better model during training, early at training. So over-parameterized here means that you need to have like actually more parameters than what you would expect. But on the other side, what you're interested to have is actually after you prune the model to still keep fine-tuning and training a bit the model so that it can recover the best performance. So given these two constraints, the best is usually to prune during training, and if possible as early as possible during training, so that basically you can also save compute not only at inference time but also at training time, because you will train a sparse model during training. Okay, so these are the main questions for how to prune models, but now we can also go to another family of methods, which is how to quantize deep learning models. So quantization in general, the concept is quite simple. So you try to transform some tensor or matrix with high precision in some other tensor or matrix with lower precisions. And here, for example, we show like just a diagram for a linear quantization from float 32 to int 3, where basically we take every weight values and scale them down based on the max and mean values of the weights, and just rounded them up to the closest integer. So here, after this step, basically what you would have is actually a matrix of the same size, but where each rectangle has a smaller memory impact. So it's only in 3 instead of 32 bits. Something which is important to know with quantization is that you do not get, out of the box speedups, contrary to what you can think. You can think, okay, I have smaller models, but actually sometimes you get slower models, because if you do like in 3 matrix multiplication on some the specific GPUs, there are no, the hardware does not support this type of instructions. So if you want the hardware to support this, the specific GPU you have to support this, you would have to implement what is called like kernels, so that it will support operations for the specific hardware and be optimized so that it does not manipulate, unnecessary bits, so to say. So there are again also like a lot of practical questions. First question is what structure to quantize. So a default way to a standard way to do it is just to take the full matrix and use the same quantization scheme for the full matrix. But usually this is too aggressive, and you will lose a lot of accuracy. So what you can do instead, you just use a different quantization scheme for each channel or each group of weights. Usually, I don't know, it can be 126 weights or something like this. And you have like a different quantization scheme for each of them. Another important distinction is that you don't have only to quantize only the weights, you can also quantize the activations. And the quantizing the activations can be also interesting, especially when you have like a very high GPU compute workload, and you have very small, data movement between the CPU and the GPU. I can talk also about like some other methods that try to protect just a very, like, let's say 1% of the weights. And this is very important when you manage to protect just 1% of the weights, because you can keep almost the best accuracy by just quantizing the left 99% of the weights. But you have to decide, wisely what are the 1% that you need to protect in this phase. Another question which is pretty important is similarly to pruning. So how to quantize structures. So here we've seen the linear quantization scheme. Basically, this is let's say the standard one, but you can actually get more involved linear quantization. You might have heard of some methods called GPTQ, for example, where you basically quantize a group of weights and then adapt the rest of the weights which are not quantized to recover from the quantization error. But there are also a lot of other preprocessing that you can do. For example, you can do something called incoherence preprocessing, where basically you get better distribution of the weights which are easier to quantize. Another family of methods, which are not linear quantizations, are called codebook quantizations, where instead of just having uniformly quantized values over the real line, so to say, you can learn exactly the quantized values so that it's not uniformly distributed. And usually this can get also like much better, performance in terms you can make the model slower, but still maintain good accuracy. One downside is, of course, you have to do some, let's say, fine-tuning step. The next question is, of course, what precision to quantize. So similarly to pruning, where you cannot prune like to 100%, for quantization, you have to decide, if you want to prune to 16 or 1 bit. And this, again, depends on the complexity of the task. If you work on MNIST, I guess you do not. But if you work on MNIST, basically, you can work to 1 bit. It will work. But if you work with LLMs, usually it's quite hard to get below 4-bit quantization on a pre-trained model. The next question is also when to quantize. So one thing that can help to get better quantization results is actually to just simulate quantization during training, so that when you quantize for real the model after training, basically, you will actually get a better quantized model. So this is one way to do it, but the downside is, of course, you need to take care of the model from scratch, from the beginning before training the model. And this is something sometimes you don't want to do. For example, when you have a lot of Hugging Face models, you just want to quantize them directly. And in this case, you would use something called post-training quantization. The last family of compression methods that we'll talk about is knowledge distillation, which consists in training a so-called student model, where we distill information from another model, which is usually a larger model, a pre-trained model, which is called teacher model. And while on the paper it's pretty simple to explain, it's actually very complex and expensive because you need to train again this model from scratch, and there are many degrees of freedom. So some practical questions related to these methods are what information to distill. So you can, for example, distill the information by just taking the output predictions of the teacher model and use these output predictions to train the student model. So this is called distilling the response. But you can also do more fancy, distillation, for example, distilling the intermediate features of the teacher model in the student model, or distilling even the weights or the gradient information, and some more complex things like this. Another question is what model to distill into. So you have to decide what would be the student model, and there are many degrees of freedom because there are many different architectures, different size of architectures, different precision. I would say the main thing to keep in mind when doing this is that the capacity gap between the teacher and the student model should not be too large, otherwise you will lose accuracy. And what people propose is sometimes actually to do it gradually. So to first distill to what is called an assistant model, then to another assistant model, and so on, until you distill to the final student model. And the last question is, of course, like when to distill the models. Again, what you can do is you can distill the models offline, meaning you train the teacher model, and then you can just after training of the teacher model, you can train the student model with by distilling information. But another approach is just to train them jointly, which is called online training. But in this case, you have like even more cost because you have to train 2 models instead of 1. So this is the brief, overview of the compression methods. I'm happy to go more into details later if you want to. But now, I guess one question is, how well does these compression methods work? So usually, I will just try to show, a couple of metrics to give a quick glimpse of what results you can get by applying each of these methods individually. So for example, if you apply, for example, just pruning on, computer vision models, you can still get time to speed up and still a pretty good accuracy compared to the base model. If you apply quantization speedups, quantization to LLMs, you can also get like time to speedups while still maintaining the same perplexity, which is the quality metric for the LLM in this case. And you can also get time to speedups for example, image generation while still maintaining the same image quality. So what shows these results is that you can get some efficiency gains with this type of when applying these methods individually. But the thing is that there are way more than just these 3 individual methods. There are many, many compression methods that you can use. And also what you can do is you can combine these compression methods. So this is exactly what we do at Pruna. And by doing this, we can get much better results in terms of efficiency gains and so on. And also another thing which is very important is that by combining also like a lot of compression methods, you can cover many more cases, which means like many more different hardware, many more different models, which are important, many different also metrics, which are important for your real world application. So the main message here is that compression of deep learning models is very complex because they are like a very huge space of compression methods that you can apply, and you can also combine them, and you can get also like problems when combining them, like methods which have like constraints that look not compatible, but actually they can be. So maybe next question is, because we discussed about quality, and sometimes quality we represent them as basically these proxy metrics like accuracy and so on. But the best evaluation is usually to have human-based evaluation. So here there are 2 images, and I would like just to ask you one question. So who thinks in the audience that the left images is the best quality? Maybe you can raise your hand. Okay. Who thinks the right image is the best quality? Okay, a bit more. Who thinks it's the same quality? Okay, so I like this test because on the right side, this is the image generated by the compressed model by Pruna. And there is almost no difference, but actually it was generated way more efficiently, like with huge speedups and so on. Just for fun, I did a second one. So who thinks that the left image is the best quality? Right image? Okay, same quality? Okay, so again, I didn't trick you. Again, the right one is actually the one generated by Pruna. So the core message here is basically to say that sometimes you can think, yeah, go ahead. Yeah. Yes, that's a very good point. Sometimes it does some very small, changes. You can also ensure for some compression methods that you get really exactly the same output. But sometimes actually people care not about getting exactly the same output, but actually the same quality. So in this case, actually, I think when I counted here, like there were a bit of people that were saying, I prefer the second one. So that's actually quite cool, I think. But the main message, as you mentioned, is that compression methods does not mean that you will lose quality of your predictions and accuracy, and you can do it without quality loss. So next, I have like, I know that there are like quite some technical people here, so I wanted to actually share like a small demo video, but maybe it's a bit too small. I don't know, I would like to ask if everyone can see this. Okay, maybe I will just skip it then, but I'm happy to maybe maybe I can just run it and try to explain orally a bit like the things. Okay. Sounds good. So maybe just before I start, so here I will just show a short demo how basically it works to compress a model with Pruna. So here we just focus on a stable diffusion model. So it's just a basic one. So what we do first is basically we just load the model, which is what is shown here, and it takes a bit of time. So that's why I did it before. And then with this step, basically, we just generate images to see what is the speed of the model at that time. So here you can see it will just generate like a couple of images. The prompt was a bucket of fruit. And you will see it takes around like, in average, like 3 seconds. I think a bit more for the first image and a bit less for the last image, which is expected. And basically what you do if you want to compress the model is you just apply two steps. You just define what we call a smash config, which is the configuration for the compression. And here we combine just two compression methods. And then we simply call just a single line saying, okay, smash this model with this smash config. And actually in these cases, it's very quick. It takes just a couple of seconds. And then you get like the compressed model, and we'll just regenerate like 5 images similarly to the previous one with the same prompt to see how fast it is. So again, the first image takes always like a bit more time because the GPU needs to warm up. But then you can see basically the GPUs, even visually, you can see that it goes faster and faster. And it takes just 1 second instead of approximately 3 seconds before. So this is very simple steps how to make, like any machine learning models faster by just adding, these couple of lines of codes. So basically, if you want to change this for like a different models, you just need to change how you load the model, how you generate the predictions, and that's it. Okay, so I will just move. Okay, so now again to the question how to compress your own deep learning models. So there are like 2 main solutions that I could see right now is like you can do the manual solution where you basically read and understand research papers. You implement and test the compression methods. You integrate these compression methods for the specific model on hardware where you have to adapt to it. Test and evaluate all hyperparameters. And then I say all the time, hopefully get efficiency gains, because in many cases you read a paper and you think, okay, it will work, and actually it will not work because, I don't know, you don't have the kernel, and so on. So the other option, I guess you guessed what was the other option is, applying Pruna, so which is simply install Pruna package, smash your AI model, and then gain significantly efficiency gains. So hence, instead of long research, basically you can research exploration. What you have is like a lot of compression methods that you can access and combine. What you have also is instead of like painful, debugging for the specific hardware and model you have like adaptability because you have like a lot of compression methods that can be applied. And also, instead of wasting resources in non-optimal, efficiency gains, you can just have reliable efficiency gains, which are, tested already on many models. And when I say on many models, it's really many models because we are, the top 1 contributor on Hugging Face with more than 6,400 models. And basically, we took a lot of models from different categories: image generations, video generations, LLMs, computer visions. We took them and we compressed them and we kind of show, okay, what you can expect when you apply different compression methods in different scenarios. So feel free to go here and test them. You can also test this demo, I think, right now if you go to the documentation. And I think that would be it for me. Thank you for your attention.
Thank you, Bertrand. We'll open up for questions. So any questions out there? Yep, we got Lele.
Thanks for your presentation. Very interesting. Actually, I was amazed about the, demonstrated result about like combination of different methods that can actually achieve a much better result. Can you actually go a bit deeper into how this combination is usually done? Are there any principles? It sounds to me like an optimization problem in itself to find the best way of combining those technologies. Yeah, I just want to learn a bit more about how you usually tackle that combination problem.
Yes, it's a very good question. So I guess there are like, as you mentioned, when you think about combination, there is like a very huge search space because for each one there is the number of methods you can apply, the order of the methods you can apply, and so on. So what a first way to approach it is, of course, to be able to train on many models and then collect data on what works and what does not work, because what you care in the end is the real efficiency gains that occurs in the final applications. So you have to collect kind of all the data and see what really works and what does not work. Then there are also like some logic into it. For example, there is the compilation methods, where it's harder to, it's not possible to apply, pruning after compilation, because you can apply, you can prune models easily on, your PyTorch models, but after it's compiled, you get some very weird code, so to say, and it's much harder to apply it. Some methods, for example, they expect to have non-quantized models, so then you cannot get, you can not quantize the models before applying these compression methods. For example, there are a lot of small logic here to find the smart way to combine the methods. And then the other thing is basically we have like also an automatic way to search into the combination space. So basically, if I go a bit technical, it's called like a kind of a bit Bayesian optimization process, where basically you can show some prior in some compression methods that would be the best to try first and so on, and then it will search smartly a bit what are the best compression methods to apply. But there is really a mix of heuristics and also automatic things, because sometimes automatic Bayesian optimization, they will miss the obvious things because it takes too much time.
Sure. Thanks.
Thank you. Very interesting presentation. It was quite impressive to see the performance gains that you saw when you compared. You showed three comparisons of base models against the Pruna improved or pruned models. So I was quite curious in how this generalizes. Specifically, do you see that your methods work better for models of certain sizes? And more specific than that, I'm thinking for very large models or very small models now, which are quite, well, they're in right now. Do you see that do you still see the same kind of gains, or do you see that these methods work better for certain types of or sizes of models?
Mm-hmm. So that's a very good question. So basically, we try to have like again a lot of compression methods so that it can adapt to different size, different architecture, and so on. And maybe the best is just to give some examples where basically we applied, for example, our compression methods on LLMs, and at some point Mistral came out, and we wanted to show that it can adapt quickly. So we just compressed it directly and put it on the same day, and it was showing exactly the same gains. Another common example is you might know like Stable Diffusion, but there is also the Flux model, which is another good model to generate images. And basically, we just, again, we applied our methods to show that basically we can also get the significant efficiency gains on the Flux models. So basically, it really adapts also to future architecture, because even though we really remarket kind of new models, they are always the same, core principles in these models.
Yep.
Thank you for the great presentation, Bertrand. One quick question is, do you have theoretical guarantees on the effect of pruning? Like now, you are generating images, that's cool. But if you go to healthcare or whatever finance, how do I guarantee that my performance, I won't have any hallucination after doing the pruning in a real environment? Do you have like theoretical stuff on that, or is it that?
So theoretical stuff?
Yeah. Do you have like theoretical upper bound on what will be the difference in terms of accuracy?
Yes. So if you want really some very technical things, we mentioned like one paper, I think, which is here. I think this would be really what you are looking at, like how sparse can we prune a GPU models foundation limit viewpoints. And this is exactly gives some theoretical points on how much you can expect to lose in the worst case when you prune this amount of the model. Maybe to say something else is apart from pruning, there are different types of compression methods. There are some compression methods like pruning where you can get some small difference in the output, but there are also some other parts like compilation. If you do in the right way, there will be no change in the output predictions. So just saying that you can also make sure for these critical use cases that you will not get any loss when you apply compression.
Yeah.
Yep. A question, thanks for the presentation. Is there a way to selectively decide what to kind of, I think, oversimplify, get rid of? So large language models, they have mathematical capabilities, coding, multiple languages. So can you prune a model, reduce a model, gain efficiency by only getting rid of what you would not need? Say you only want a model to not lose anything on finance domain. Can you do that?
So it's also a very good question. So basically, there are some methods, compression methods, which are like data free, and some methods which are not data free. And what you can do is for methods which are not data free, you can give this data information so that the model will select the most important parts based on the data that it observed. So this is also something which is really important when you fine-tune the models. You can, for example, prune the models, and then you can fine-tune the models to just recover the performance on this specific application. So this is something very important because in many cases, you don't need to have the large llama, in a hospital that is able to answer what is the president of the US, but you just need the llama model to be able to answer, medical related things. So you can make specialized models and make it focusing on, the core part of it.
Thank you for important work that you are doing. I was just thinking, going to market, you have some 1,000 pre-shrinked models out there. But then if I want to use your services and have models that I want to shrink down to get on like an IoT device or something, how will that work? I mean, you say, talk to me on your website, but you don't have a web service or anything like that up and running yet where I can post a model and get it optimized?
Actually, if you want to, you can just try this demo, and basically you will get a token to just try this on your model. So you can just try this, and if you get like some interesting things that you're interested to explore, some directions, I don't know, some things maybe in the problem the installation, I think we are very happy, to just collect, any feedback to get this better and more easier to use.
I have another question, which is maybe arguably a bit outside of this scope, but like very close too. I realize because personally I'm super interested in AI-generated content detection, and in computer vision or large language model, there is a particular type of method which is basically injecting some kind of watermark into the contents. I wonder, actually, because the work that you guys is doing is also changing, you can say, a bit of the distribution of weights in some way. So in that sense, have you seen any work that is trying to combine these two efforts, basically compressing the model and also injecting a bit of distribution shift into one work, so that we have one stone, two birds? I kind of have a rough feeling this could be something that may be doable. I'm not sure, because you have been working in this domain for quite some time. I wonder if you have seen anything like that.
So what would be the goal of having this distribution shift after the compression? Maybe if you can elaborate.
Yeah, so the usual way of enabling, detecting, or telling whether a content, like an image, is generated by AI model is trying to add a bit of pattern in, for example, the distribution of pixels. And that is actually can be done by manipulating a bit of the model weights. And in this model compression work, you are actually also changing a bit of the model weights. For example, quantizing the weights. I wonder, like, without sort of jeopardizing or harming the output quality a lot, whether you can combine these two work together. Any research that you have been seeing?
So
this is just my speculation, by the way.
I don't have any papers in my mind right now, so I prefer not to make any strong statement here. But I guess it sounds indeed very related. But I don't have like strong papers in my head, so prefer not to be overconfident on this.
Oh, that's fine. Thanks.
Okay.
You mentioned earlier that it's possible to also compress a model during training already.
Yeah.
Is that something that Pruna supports as well? Or what would you recommend someone who first wants to fine-tune a language model and then deploy it compressed, but in the best case also fine-tune it compressed?
So actually, right now we really focus on making inference more efficient, but we are also working on some incoming features or being able to specialize on some specific domain and so on. So which are called this parameter efficient fine tuning. So this is definitely something it's not right now in Pruna, but you can just take the Prune models and fine tune yourself. But we work on making this even easier to use because sometimes it's a lot of playing around to make these steps.
Thank you for the presentation. I was wondering if there's some architectures that are more prunable than others, like some specific features. If you compare like a vision transformer or a CNN, what would be the most prunable architecture?
So if we focus just on the pruning methods, for example, computer vision models, they are quite good at pruning. I mean, quite easy to prune, so to say. In comparison, LLMs, because also they store like a lot of useless information as well, and they're not super specialized. If you want to keep like a very general LLM, you cannot prune as much as possible. But there are always like some other methods that indeed like cover this, other models. For example, quantization works quite well for LLMs, but you can do also a lot of compilation, batching, caching, a lot of things. So I could say it depends, as I mentioned before, it depends really on the complexity of the task. So LLMs, they try to solve a much more complex task than computer visions that try to detect, segment pixels and so on.
Thank you.
Cool. I think we've exhausted the questions for now, but I'd like to thank again Bertrand. Thank you so much. So a round of applause for Bertrand. And yeah, so we'll be here still. So feel free to ask him any questions and see how you can smash your models as well. All right. So thank you so much. Thank you.
Thank you.